Here we have a block that's released from rest at point A. Well, where in the world is point A? Let's add in point A here. Point A is going to be right here. So right there at the top. The incline is frictionless, and the block slides down to point B, which is going to be right here. And then the block comes to rest at point C, which looks like it's going to be right there. So this is a flat, rough track between B to C. Let's draw energy bar charts for this situation. We have some kind of height here. It is elevated, so that means we know for sure we have gravitational potential energy. It's also released from rest, so we know for sure there is no kinetic energy. Well, how much is enough? Whatever you want. If you go all the way up to 10 like I did here, that's great. If not, that's fine. You can still track the energy no matter how much there is. So at point B, all of that gravitational potential energy has been transformed into kinetic energy by gravity doing positive work on it. So gravitational potential energy has been transformed into kinetic energy. Is there any gravitational potential energy right here? No, we're going to say this is our height equals 0 point right there. So that means all of our energy is now kinetic energy. And then from B to C, the flat, rough track, that means the kinetic energy is going to completely disappear. Let's see. Oh, comes to rest. So yes, we have no kinetic energy. We have no gravitational potential energy. Certainly there's no spring potential energy. That means all of our energy has left the system and is now in the environment thanks to friction doing work on the block to transform that energy out. So let's go ahead and take a look at the weight in the tables below. Each possible system, draw plus or minus or 0 to state the work done by each force during each interval, and state what energy transfer, if any, that force is responsible for. Also state whether mechanical energy of the system increases, decreases, or remains the same. Well, we know it's going to remain the same if there's no work being done. So the only way to increase mechanical energy of a system is to have an external force acting in the same direction as your displacement. That will add in energy to the system. Meanwhile, if you have an external force acting in the opposite direction, opposite direction of your displacement, you're going to remove energy from the system. So let's see. The weight force. Yes, the old weight force. At the top, if we just drew our force here, we have the weight force, Fg, and then we have the normal force. And if you can imagine, as this block slides down this incline, that normal force is going to be pointed towards the center. So, hey, this is kind of like a circle, so that would have something to do with your centripetal force here. We'll see if that matters. All right, so now we have the chart down here. So the weight force between A to B, the weight force is pulling it down, and in fact, this block is going down and to the left, right? So the angle between our displacement and our force, this angle right here, is acute. So that means weight is doing positive work to transform gravitational potential energy into kinetic energy. We'll just stay in between A and B, and then we'll go to B and C. Oh, this is important. Holy cow. The system consisting of only the block. So only the block is the system. Weight is an external force. So we're increasing the amount of energy, right? Right. So if we're only looking at the block, then only the kinetic energy is really what's happening, or what's going to be changed. Because remember, if we don't have the Earth as part of our system, we do not have gravitational potential energy within that system. So the normal force, by definition, is normal, so is 90 degrees from the surface. So if the normal force is going up this way and then weight is going down, normal force is not doing any kind of work. So it's not transforming any energies, it's not adding any energies, it's not taking away, it's just kind of there. So that's because the angle is obtuse, remember. So we've got an obtuse angle here. This was an acute angle. Frictional force. Well, between A to B, there is no friction, so we don't care about that. The net force is positive. Because if you think about it, if we consider the forces acting, which are the weight force and the normal force is not doing any kind of work, so that means the net work done would also be positive. And that means the net force is also positive. We can also note that the net work done is also positive. All right, between B and C, again, the system is only the block. Between B and C, the weight force is not doing any work. It's no energy transferred here. The weight force has nothing to do with this. Of course, if we increase the mass, then that changes the weight force, which would then change the coefficient or change the frictional force. So yes, you can get there, but strictly speaking, the weight force is not changing any energies. The normal force is perpendicular to the displacement, because the normal force at this point is going up, displacement is to the right. So 90 degrees means no work done, no work. Frictional force here. Frictional force is stealing that energy. That's what's slowing it down. So it's transferring that kinetic energy that we have at point B into the dissipated energy. The total mechanical energy is going to decrease because we have dissipated energy. So the total mechanical energy decreases, which means our net work is negative or decreasing. Now, with the block Earth system, this weight force is brought on by the Earth, right? So now this weight force is internal. And internally, if there are forces acting, it's not doing anything affecting your displacement or affecting your motion. So the weight force is not doing any work. Let's revisit over here to think about this more specifically. The total energy for this system is only related to the kinetic energy because it's only the block system. Meanwhile, if we have the block Earth system, now we have kinetic energy and gravitational potential energy within the system already. So that means our total mechanical energy here is already this. The weight force is transferring the gravitational potential energy into kinetic energy. Yes, that's still true, but it's not doing work to add in mechanical energy or take away energy. Normal force, you already know. It's still zero by definition. There is no energy. The displacement is always about 90 degrees. To the normal force acting. So there is no energy involved here. Frictional force, we have no friction between A to B. The net force, there is nothing external to this system, to the block Earth system, doing any work. So the energy stays the same. The energy is constant. Meanwhile, between B to C, gravitational potential energy, again, does not affect the slowdown from B to C. So there is no energy transfer happening here.